given epsilon, suppose if I say epsilon is equal to 1 centimeters, I have given. So in this case, I have given epsilon is equal to 1 centimeter. So the minimum number of points in epsilon. So if I draw a circle, with this as a centroid and with this epsilon radius, if I draw a circle, then how many number of points fall in this circumference, under this circumference region? So fall in this circumference, under this circumference region. So that is called the minimum number of points. If I given an epsilon and given a minimum number of points, so these are two hyperparameters for any density based clustering, because this will define the density. Yes, definitely, because what is the epsilon? Suppose if I standardly I have taken 1 kilometer. One this is if I say if I'm taking another, this is 1 kilometer. So minimum number of if you take population, number of people. That is it. These two parameters are very, very important to define the density, right? So it need not to be compulsory 1 kilometer. I can take what you say 1 meter or so 1 square. So in a given certain metric, I mean with a certain distance metric. So within this distance, how many people are staying? That's the minimum number of points. That way you can map it. So this together will define the density. It means that these two are the hyperparameters for any density-based clustering algorithms, right? Now let us come to the another parameter is called epsilon neighborhood. This is denoted as n epsilon p. So what is this? So Q belongs to the D. So it means that if epsilon neighborhood P means that Q belongs to D if and only if the distance from this P and Q, the distance from P and Q is less than or equal to epsilon. What does it mean? It means that if I draw a circle, this is my P. I said that this is my epsilon. This is my epsilon. So maybe the P as a center with the epsilon as a radius, I have drawn one circle, right? Now what I'm saying that there is a point Q. The distance from this point Q, distance of P comma Q is less than or equal to EPS. So it means that this Q is in the epsilon neighborhood of P. It means that the D is inside the circumference of the P with a radius of a epsilon. It means that we can say it as an epsilon neighborhood, where epsilon is the radius. It means the P is the point is in the neighborhood of region of the P. This is denoted as neighborhood of epsilon with a point P. Right. Now, so let us discuss what is directly density reachable. A point P is directly density reachable from a point Q with respect to the epsilon and minimum number of points if the P belongs to the epsilon neighborhood of Q and it should be the core condition. What they are saying that if there is a point P, so if there is a point Q and there is a point Q. So what is the relation between these 2 points? If you want to, so if they are directly density reachable, they are DDR means a point P is directly density reachable from a point Q. So point Q with respect to the epsilon and the minimum number of points, if this P belongs to the epsilon root of Q, means when I draw a circle, Q as a center with epsilon, yes, this epsilon, what is the epsilon? 1 centimeter radius, this is that circle. If I draw a circle with epsilon neighborhood, with epsilon as a radius and the Q as a center, then where this P should be? This P should be in the neighborhood of P. The P is the neighborhood of the Q. So it means that it should be either on the circumference or inside the circumference. So when I draw, it means that the distance from these 2 points, the distance of this P comma Q is less than or equal to EPS. This condition. It should satisfy this condition, this first point. And also what it is saying that the point Q should be a core point. So what is the core point? I think we didn't come across this core point definitely. So what is the core point? If P should be core point, if and only if it is having in its neighborhood, the neighborhood of Q with the epsilon radius, if it is having the number of points inside this is the more than the minimum number of points. Suppose in the epsilon neighborhood of Q, if you draw a circle with the epsilon radius, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points are there, which are greater than or equal. What is the minimum number of points you have defined? 5. It means that if any point in its neighborhood with such radius, with such epsilon radius, if you draw a circle, if the number of points inside this neighborhood is more than the minimum number of points, we can say that that is a core point or some important point. It's that we can, it is indirectly mean, it's indirectly giving intuition that this point is somewhat densely reachable. This point is density. Okay, this is density point. We can say, we can visualize like that. We can right, because this is surrounded by more points. Hence, we can say this point has some a density point. Okay, like that. So this is the definition for the directly density reachable. Okay, so if there is a point QP, and if you want to reach from Q, so this should be in the epsilon neighborhood, as well as the point from where it is, the point where Q should be the core point, should be core point. Now, what is the directly, we have seen what are directly density reachable points. What are the density reachable points? So if you want to define the density reachable points, a point P is density reachable point from a point Q with respect to epsilon minimum number of points if there is a chain of core points. If there is a points P1, P2, P3 and so on, and such that what they are saying, the P is a directly density reachable P. It means that here in the earlier case, you have the Q and a P. So this P should be the core point. I mean, this Q should be core point and P should be in the neighborhood of O. That's what we have seen. But what is this? This is, as there is, we can say just it is in only one half distance. It's a one in it just it's in its own neighborhood. It's an own neighborhood. That's why it is called directly. We can directly reach from my own points. That's why it's a directly density reachable. But where in the case of it's not directly density, it's a direct density reachable. In that case, if this is the Q and the P is somewhere here, this is not directly density. There is a chain of points like it's a P1, the P2, and P3 and P4. And this P1, P2, P3 should be core points, as well as they are. Suppose if I draw a circle, so this Q should be in the neighborhood of Q, and this Q should be, so this Q should be core point. Then if I draw a circle with this is a center, this Q should be in the neighborhood, this P2 should be in the neighborhood, and this P1 should be a core point. So then only it's called, we can say Q and P are directly density reachable. This is directly DDR. Hope you are understand. So this is DDR, and with respect to these two, they are directly density. So there are chain of points which are directly density reachable. Hence, we can say that I can reach this P indirectly, not direct. That's why it is called density reachable point. Now, the density connected points. What are the density connected points? So there is a points P and Q, and there exists a point O such that from O, this point P is density reachable, and this point is Q is density reachable. A point P is density connected to a point Q. Density point to a point Q with respect to the epsilon and minimum number of points. If there is a point O such that the both P and Q are density reachable from O with respect to the epsilon. What they are saying that, so there is no direct, there is no they are indirectly density reachable. Okay, but this point P is density reachable from O, and same the point Q. So there exists a point O such that, so from O to Q, it's a direct density reachable, and from this to point Q, this is in that case, what we can say that, so this P and Q is connecting with some set of points. So these points will are the core points, and this will form a density region. So a core point, what does it mean? I said that's it's a point which is surrounded by density points. Okay, its core point is means that, okay, it means that there exists a set of core points in this is like this. You can visualize, okay, like this kind of. So this is a Q point will be here, and P point somewhere, P is here, and this is directly region. So it means that it is connecting to density connected region. The two density reachable region. So hence it is a density connected. So this point is acting as a connecting these two regions. So this is one particular region, so which is density reachable, and this particular region is a one particular density. So these two regions I'm connecting. That's why it's called density connected. This point P is acting as a middle point, so which will connect these two the regions. That's why like that you can visualize. Now, so we have seen so many definitions. So many definitions related to the density-based clustering algorithm. So, like we started with the what is the minimum points, what is the epsilon, then we have defined what is the core point, what is the epsilon neighborhood. Then we have discussed about what is directly density reachable, then density reachable, and then density connected. Then by using these definitions, in how can we build the clustering algorithm? That's what is the next slides. Now see, so let's see. So what, how the DB scan works? Okay, so DB scan means density-based spatial clustering of application with the noisy. So this is the definition of the DB scan. So this algorithm, so this density-based algorithm are cleverly handles the noisy. So this noisy, I said, it is an outlier. How? So realize in a density-based notation of the clusters, a cluster is defined as the maximal set of density connected points. How we can define the cluster? What is meant by cluster? The cluster is nothing but a set of such density connected points. Set of, so this has interlinked to this, and this has interlinked to this. So this is interlinking. So if you want to define density connected regions, then you must know what is the density reachable region. If you want to define what are density reachable regions, you must know directly. So that there is a chain of connections to this. Okay, so how can I define the density connected points? Okay, so the set of maximal set of such kind of density connected points is togetherly formed as the cluster. Okay, so our idea is to form out this such kind of identify such kind of the points and make it as a group. So with this, we can say that this particular algorithm will definitely identify the shapes of the arbitrary shape. It need not to be convex and convex shape. It can be of any shape, but this particular clustering algorithm is able to. So if you want to assess the clustering algorithm, so one of the parameter is whether this clustering algorithm handles the whether this clustering algorithm will able to identify the clusters of different shapes. So that's one of the parameter to assess your clustering algorithm also. So with respect to that particular point, I mean, whether it's so definitely this algorithm will able to identify the clusters of different shapes. Now let's see how DB scanner. So I said in our superficial, in the outline, in a nutshell, I kept that the DB scan is able to identify the points which are density connected. Okay, its idea is to find out the density connected points, and such density connected points will together form the cluster. Okay. Now see, arbitrarily select a point P. Arbitrarily select a point P. Somewhere you start the P and retrieve all points that are density reachable from P with respect to them. So this epsilon and the minimum number of points are two hyperparameters. So means what is hyperparameters? These two hyperparameters as to supply by user and supply by the programmer or the one who is dealing with this algorithm. Okay. So retrieve all the density reachable points, the directly points P with respect to the epsilon and the minimum points. If P is a core point, a cluster is the form. Okay, so once this cluster is formed, then again you can merge this cluster with the another cluster. If the P is a border point, so no points are density reachable from P, and the DB scan visits the next point. So what does it mean? That so first it will start from the one point, it will start exploring like this. So once it is a border point, it will stop its algorithm. Then it will select another point. It will keep on exploring like this. That is the way it will work. So continue the process until all the points have been processed. First, you will start with one point to start exploring. It will start exploring, finding out the density reachable points. So as long as it's able to get the density reachable points, it will create the cluster. So once it identifies the border point, once it's so how do you define the border point? If it is not a core point, definitely is a if it is not a core point, it means a border point. Okay, so if there is no minimum number of points, enough number of points inside your cluster neighborhood, then it's a border point. Okay, it means what is meant by it indirectly means that it is not surrounded by more data points, we can say it is not a density. It's not a density point. Okay, like that we can say. And this process is continue until your all the points have been explored. So as I mentioned that, so this DB scan algorithm is able to identify the clusters of a different shape. See, if there are different shapes. This is a different shape, triangle shape. So it's able to identify the clusters of different shapes, need not be convex. But if you see what this figure shows that this algorithm, the DB scan algorithm, is sensitive to the two parameters. What are the two parameters? The one is epsilon, other one is minimum points. You should cleverly choose these 2 point values. That is the duty of the one who is dealing this algorithm. If you don't set this algorithm properly, this parameter values properly, you will end up with the wrong clusters. That's what the figure shows. If you see, for some certain value of so here I said the minimum number of points 4 and epsilon at 0.5 and 0.4. For 0.5, this is the output we got. For 0.4, so if you see, so many clusters have been formed. So you should be cleverly. For the same way, minimum number of points, for the minimum number of points for 5, so it has created two clusters. The minimum number of points is reduced to the 3.53, something like this. So it has created this kind of clusters for 3. It has created these many number of clusters. This many number of. So it means that if you change this value, the output, what is the output? The number of clusters is also affected. Hence, you should cleverly choose this epsilon and minimum points. So that's why it is called hyperparameter. It's the duty of the program. Yes. So let us look at another algorithm is called the optics. So with this I will stop. So this optics is another clustering algorithm which is based on the density. Okay. So idea is very simple. So if you see here, apart from whatever terminology we have studied, along with this, so we have some more terminology which is particularly useful in this algorithm is, so what is called a core distance. So how this algorithm works? What is the core distance? The core distance is the distance from the epsilon to the core points. If there is a point, the distance to a particular point to a core point is called the core, the distance. So what is the reachability distance? So reachability distance is the maximum of the maximum of the core distance as well as the actual distance, whichever is the maximum. So that is your the core what is called reachability distance. So what is the use of this reachability distance? I will explain in the next slide. So if you want to find out the reachability distance, you must know the core, the distance. So what is the core distance? What is the minimum epsilon is required such that there is a point. This is a point. So this is epsilon. So what is the epsilon value? What is the epsilon value? You have to set such that this point will become the core point. This point become the core, the point. So the minimum epsilon, what is the minimum radius is required to be qualified a point as a core point. So that's what it's called, the core distance. It's clear, right? Now see, so what is the advantage of this reachability distance? If you see from this figure, it's why. So once what we will do in this optics algorithm, so we will find out the reachability distance of every point. So there are points. So this is the point. So we will find the reachability distance of every point. We will find out the reachability distance of the every point, and we will arrange them in a ascending order. We will arrange them in some sort order. Okay, ascending or descending order, according to the reachability distance. Okay, according to the reachability distance. That's why we will have some order. Okay, cluster order of the objects. Okay, we will order this order these data points according to the reachability distance. So this is reachability value. Now, so you can observe one interesting pattern in this plot. So this is called a reachability plot. Okay, so in this case of reachability plot, what will happen? So you can notice some kind of caves. This is one cave. This is another cave. This is another cave. So this each cave corresponds to the one cluster. Just Our problem is solved. So we are able to find out the, so this is one cluster, this is another cluster, this is the points which are pertaining to this belongs to one cluster, and the points which are forming this particular cave, it belongs to that particular cluster. These points are belongs to this cluster. So right. So what we are doing here? So what we are doing is, so we are finding the reachability distance and we are arranging them in certain order, either increasing or decreasing order. Then in the reachability plot, so this in the reachability plot, you will find some interesting caves. Okay, these caves are corresponding to the clusters. So there are three caves are there. We can say that there are three clusters are being there inside your data. Right. Now see, there is one hyperparameter. So it means that, so what could be the limit of this, what is the limit of this reachable rate? So where should I cut down this my graph? Okay, so that I can see the number of the clusters. Suppose if I cut here, I can see 1, 2, 3. So if I cut at this position, I can get 1, 2, 3, 4 clusters. Okay, so you must have some value for this epsilon, so that where do I cut my reachability plot, so that I can get the required number of the cluster. So you should be, this is the hyperparameter again. You should cleverly cut this. Otherwise, suppose if you cut here in this point, it will have the three clusters. If you cut the above, it will have the 4 clusters have been formed. So you should have cleverly choose this epsilon value. Right. So this is some related to the basics related to the density-based clustering, and I won't discuss about the grid-based methods. So let us go into the evaluation of the clustering techniques, and then we will move on to the cluster validity indices. Okay. So now let us come to the actual topic, cluster validity indices. So what is the cluster validity indices? What is the purpose? So if you say, in case of supervised learning, like the classification, so you have certain metrics. With the help of these metrics, we can evaluate your clustering algorithm, classification algorithm. The similar lines, so there is a clustering algorithm, there is a supervised algorithm, unsupervised algorithm. Then how do we evaluate it, whether this algorithm is up to the mark or not? How do we evaluate? So for that, there is some certain measures have been defined in literature. So let us discuss about this. The cluster analysis or clustering is a task of grouping a set of objects in such a way that the objects here belong to the same group, and this group will have certain similarity common across all these group members. Okay. So usually clustering outcome is tested with a qualifying measure. So that measure is called clustering value. The same thing what I said. So to evaluate the outcome of this, the output of your clustering algorithm, so you must have some measure or some metric. So these cluster validity indices are meant for that. Okay. These cluster value indices measures precisely how well the clustering splits the given area. Of course, well, whether your clustering algorithm as a partition your data, the group your data properly or not. So that's all about whether it's created proper clusters, the proper groups are not. The metric for evaluating the clustering algorithms. Right. So in the literature, not only there are so many other, but for today's discussion, I have taken 4 cluster validity indices, and these are inter-ratio validity indices. So one of the Doom indices, and other is the dynamic validity indices, and other one is the Davies-Bouldin index. Right, these are the indices. It's sometimes depending on the indices we are choosing. Sometimes we may look for the higher value. Some we are looking for the maximum value, or sometimes we are looking for we are maximizing certain indices, and sometimes we are minimizing certain indices. It depends. Okay. In case of inter-ratio, we are looking for it, the, the algorithm for which this indices value is the least, so that algorithm is good one. Like that, we can evaluate the outcome. Because suppose this your algorithm has generated two clusters for, so there's a clustering algorithm. It has, you said for k is equal to, it has created two clusters. For k is equal to 3, it is created 3 cluster. K is equal to 4, it is created 4 clusters, like this. So whether which one is good? So same algorithm has generated multiple outputs. Which output is good? So to evaluate that, we will use these kind of indices. Okay, we will, things will be clear as we are moving ahead. Okay. So the its objective is clear. The idea of this, all these cluster validity indices. In the beginning, I mentioned the any clustering algorithm should be defined, should be created. The cohesive clusters or the compact cluster, the cohesiveness, okay, compactness of the cluster, the overall. So it should create the intra cluster should be, the clusters should be created very compact, and the distance from this should be very far away, so that we can easily discriminate these two clusters. So this is called well separatedness. It means that overall the finest intra compact clusters, so that talks about, it means if there is a clusters, so this cluster should be very tightly packed, and there is another cluster, this is also tightly packed. But when it comes to the interclust, this is inter and this is intra. When I was talking with respect to one cluster, it should be compact. When I'm comparing two clusters, it should be well separated, so that we can easily discriminate these two clusters. Right. So let us talk about the first indices, intra-inter ratio index, and it has been proposed by the Ray and Thur. There are two scientists who have been invented this index for the purpose of the cluster evaluation, clustering algorithm evaluation. So this Ray and Thur have introduced this. It's the first time only such indices in the literature, and it has proposed Ray and Thur. Of course, it looks very simple. And how this that is defined? They have defined it's a ratio between the intra-cluster distance and the inter-cluster distance. It means that this is talking about intra-cluster distance. So for a good cluster, this should be more compact. More compact. The compact means, how do you define this compact? This talks about spread. The spread should be less. The less spread. So it means usually we are interested in the cluster which is having less intra-cluster. And when I'm talking about inter-cluster distance, so how do you look like? There are two clusters. This distance should be more. So visually we are prefer to have the less. The numerator should be less, and the denominator, ideally this should be more. In that case, the overall this measure should be have the minimum value. For which value? For which numerator and denominator value? So this intra ratio is minimum. So that is, so we are ideally looking for which this index value is minimum. So that is a good one. So that outcome is good. Right. Now, how they have defined the intra-cluster distance? It means this talks about the compactness of the cluster. If there is a cluster, so this talks about the compactness. So how they define this compactness? Now, where x is a data point here, x is a data point, something x is something here, and Zi. What is the Zi? So where x belongs to the, so where Zi is the centroid, so Z1 centroid. Z1 is centroid, and x belongs to the, what this talks about? So distance from centroid to the every point, where x belongs to the Ci centroid, x belongs to the cluster C1. Suppose x belongs to the cluster, so like this. This is x, y, z. Means from every centroid to all the points, you are finding the distance. And you are squaring it. You are finding the centroid to all the points, and you are squaring it. So this is something like what you call error, you can say, in the k means it's called error 1. Okay, and similarly we will find error 2, and similarly you will get for other cluster you will get error 3. So what they are doing here, they are averaging. So for this cluster 1, cluster 2, cluster 3, this outer loop will talk about the number of clusters. So there are 3 clusters, you are taking 1 by n means as there are. So if there are, sorry, this 1 by n, where n is the number of data points, then n is the data points. Or typically we are taking average, or we are taking the compactness. We are taking the compactness of each and every cluster. This way they have the defined the numerator of your index. So what is this intercluster distance? How they are finding the intercluster distance? They are finding the where Zi and Zj are two centroids. This is a centroid. This is the centroid. This is one cluster. Its cluster centroid is Zi. This is Zj. Now they are finding the distance from these two centroids. Just finding the Euclidean distance these two centroids. But if there are 2 clusters, it's okay. But there are 3 clusters. So this is Z1, Z2, Z3. So you have to find all possible. So you have distance from these two, distance from these two, and distance from these. Among these, which one is the minimum? If there are multiple clusters in the intra-cluster, the numerator, you have taken consideration of all the clusters. From every cluster, for every cluster, you have taken its spread or its error, and you have summed up. That's the numerator. So the comes to the denominator part, the comes to this part, denominator part, how we have calculated, there are multiple clusters are there. Then in this clusters, the one which is having the minimum, the distance, so that distance you have considered as the denominator. Right. So now, so for which value of k, if we see the k is k, for which k, for k, what we do typically, I think I forgot to keep. One second. So if you observe, so there is a k. So what we will do, we will take a, this is k is equal to 1. This is k value. K. K is equal to 1, k is equal to, k is equal to 3, k is equal to 4, k is equal to. This is the y-axis. We will take this index value, inter ratio index value. This is index value. In this case, we have ratio index. For k is equal to 1, for phi is equal, what is the k? The number of clusters. For number of clusters 1, what is this value? Suppose here, its value is this. For k is equal to, this is the value. K is equal to, this is the value. K is equal to 4, this is k is equal to 5. Suppose this is something like this. And for k is equal to 6, it is like this. K is equal to 7, it is like this. So from this, we can say that for k is equal to 5, you got minimum ratio index value, means that the best value for k is equal to 5. It means that it's all roughly, we can say that your algorithm is having roughly the 5 clusters, the groups inside your data. And we can say that for k is equal to 5, this algorithm is working good. Your algorithm is working good. Means ideally we are looking for, so this is what I mentioned in the last. So important, for a better clusters, it means that whether your algorithm is creating better clusters, how do you evaluate? It's clearly shown in the plot that the one which is giving least index value, it means that at that particular k value, your algorithm is giving best results. So we can evaluate. Now we are evaluating the clustering algorithm. Am I right or not? So for a better cluster, this validity index need to be minimized, and hence the smaller value for this index indicates that you have created good clusters. What is meant by good clusters? It means that you have created well compacted cluster, compact cluster, and the distance from the 2 clusters and multiple clusters is well separated. Means that you have well separated cluster and well compact clusters. It means that. I hope it is clear. So like this, we can use this index value to measure whether this is some algorithm. Okay, this is some clustering algorithm. For k is equal to 1, this is the performance. K is equal to, this is the performance. Everywhere we are measuring the performance with the help of this index values. In the similar lines, there is another index is called the Dune index. So it's slightly a little bit they have slightly modified what you call the intra ratio index. So what they are saying here, if you see, so this is the Dune index value, and what they have how they have formulated, they have restructured this and they're slightly modified the intra ratio index. And now let's see. So what they are talking in the numerator they are talking about the distance between the two clusters. The distance between the two clusters. So definitely when Ci and Cj when are talking, so this numerator is talking about intercluster distance and compared to the previous metric. So this is talking about the separatedness, well separatedness. This should be maximum, usually should have more value. So this is talking about the diameter. So what is the diameter? The diameter means usually a single this is cluster will have diameter. Okay, usually this is this is my diameter. This diameter is talks about the intra-cluster. It means this talks about the compactness of your cluster. Compactness of your cluster. Right. Now what we are trying to do. So in ideally, what we are trying to do. So this should be maximum, and this should be minimum. Overall, so I'm interested in more compact, more well separated cluster. That is my numerator. I'm interested in more compact. That is my denominator. So the outcome will be is it maximum or minimum? We are looking for a maximum value, minimum value.
I think minimum value.
No response. So if you see, you're ideally looking for the maximum value, where in the case of ratio index, you look for the minimum value. But if you see, so what we are trying to do, so we are to finding of, we are among all the clusters, minimum of k is equal to where NC is similar to k, NC is equal to number of clusters. For among all the clusters, k is equal to 1 to 2. The one which is having the least diameter we are taking. The one which is having the least diameter. It means that usually we are interested. You're picking up a minimum among all them. So this is minimum. And for the two clusters, the numerator numerator should be more and denominator should be the less. I mean, you are interested to this part should be maximum value and this should be minimum value, but togetherly you are looking for the maximum value. But among all such combination of the maximum values, you are looking for the minimum. So definitely, and all this you are looking for a minimum value. So means for which NC value, NC value, you are looking for for which the DNC value, the Dune index value is minimum. So that is the best output for your algorithm. So, but if you look at what is this how do you find the distance? So maybe they are some different way, but the distance between two clusters, the distance where this talks about the well separatedness. So how do you find out this? We find out the distance between 2 points x comma y, where x comma y belongs to the two different clusters. In this when this distance will be maximum, when distance will be minimum. Can anybody says there are two clusters? So this x belongs to here and y belongs to this cluster. This is Ci and Cj. So when x is here and y is here, so this distance d of x comma y will be minimum. Means when these 2 points are the border points. Is it here? Isn't it? So when these 2 points are border points, then you will have the minimum distance. So this distance with these 2 border points is called the well separatedness. If you see, it's clearly this distance will talk about the how well your clusters have been separated. It means that this usually we are prefer to have a longer distance, more distance. Now, how do you find the diameter? The diameter is the distance between the 2 points x comma y. But where in the earlier case x comma y belongs to two clusters, but here both x comma y belongs to same cluster. When this can happen, this is two extreme ends. In this case, when this x comma y will have extrema, x and y are both in the extreme ends of your cluster, then this can happen, right? I think it is minimized. Okay, sorry, it's written minimized. So this index need to be minimized to identify the compact and well separated cluster. In other words, higher value for this Dund index indicates a good estimation for fine tuning cluster number. How come it is? Yes, yes. So here is the maximum value only. So because if you see this particular thing, so let me clarify this. If you see this, I am interested in maximize this value, and this I am trying to minimize this. So overall, you are trying to maximize this particular portion. So what this both this summation, I mean, this is kind of this outer loop and inner loop will talk. So this outer argument and inner argument talks about. So among all those maximums, you are picking up the minimum. Okay, among all those. So there is a maximum one, but you are trying to maximize. But among all those maximums, so which one is the maximum? So which one is the minimum? So ideally, we are trying to maximize this value. So ideally we are interested in the value for which NC value this DNC is the maximum. So far we have seen two indices. One is the what you call ratio index, another is a dynamic Dund index. Now let us talk about the dynamic value. In the previous two indices, which have been proposed by Ray and Ture, and so there is a limitation of that it won't handle the noisy data properly. So there, in the previous cases, so if there is a noise in the data, so you will end up with the creating the wrong number of clusters, maybe. So that's why, even though so it means that those two indices won't handle the noisy data. So hence, to handle noisy data, there is a person called Jurang Shen. He has proposed this index. Actually. So this has been proposed by Jurang Shen. Okay. So this dynamic value index has been proposed by Jurang Shen to handle the noisy. So what he did is, so he has cleverly combined these two metrics. So I think the idea of all these indices is very clear. This is talks about the intra-cluster distance. This is talks about the compactness of this, talks about the well separatedness of your clusters. And these two combined the linearly by using some hyperparameter is called the delta. So what is the role of this delta? So what is the role of this delta? This delta parameter is to handle the noisy. Whether there is a noisy, so delta is equal to 1. If there is, and if there is no noisy, delta is equal. If there is a noisy, so delta value is greater than 1. Sometimes we can use delta is less than 1 also, depending on the situation. Okay? But ideally we will use delta is equal to 1 if it's there is no noisy in the data. If there is a noisy in the data, the delta is greater than 1. Right. So what we are trying to do here I'm interested to find out the index value for which this particular DV dynamic index is minimum. For which value of K, this DV index is minimum. So that is the best K we can say. Now let's see how they have defined this intra-ratio index and intra-ratio index. I mean intra-ratio. So this intra-ratio is talks about it's very clear. It talks about within the cluster. Okay. For this we have to find out the intra K and what is the maximum intra. So for particular cluster, what is its clustering K, and among all, what is the among all the cluster, which one is having the max? You are finding the ratio. You are normalizing some sort of thing. Similarly, So this is inter K and this is maximum intra. Among all these, so there are two clusters clustering distance among all the distance between two clusters. Which one is the maximum? That is the maximum intra. Okay, it's very simple. Now this talk about the intra of K. This we already defined. What is this? This we already defined in the intra ratio index. This formula, if you see, is the same as that. If you take it or not, okay. So if you right, the same as that. So what we are trying to do? So from given a point, from given centroid to all the points, it's finding the distances, and like this you repeated for the all the cluster. If there are K clusters, yes, you're finding it's a value intra of K, and the maximum intra is the maximum of intra of phi. Which one is for which way for among all these for I is equal to 1, for I is equal to 2, for I is equal to 3, for I is equal to 4, for which this intra of this particular index is maximum. So that corresponding is considered as the maximum intra. So among all possible values, which were a set of values, the maximum value is considered as the maximum intra. So coming to this, the inter ratio, this talks about the what you call the separatedness, well separatedness of your cluster. But maybe they formed in a different way, but they may restructure it. But idea is to get the this well separated cluster. Okay. So how they are finding? So that's why this particular index deals with the within the cluster. This but deals with the among the cluster. That's why we are concerned about the cluster centroids. Okay, the cluster, the centroid. So they formulate like this, and the among what they find the maximum among all these terms. So there is a two cluster centroids. There exist multiple such. Okay, so among all this, which one is the which two clusters are well separated? Which two clusters having the maximum distance, and that distance and divided by the remaining the distance among the all remaining all the clusters. Okay, the distance between all the clusters. Okay, Zi minus Zi and the square distance. Okay, so this way we can find it out. So this intra K, and this is formula just by manipulating these formulas, which is actually just we are trying to they are restructuring the intra ratio index, the beginning one, which is proposed by Ray and Ture. Just they are slightly modified. Okay, but this thing, the beauty of this dynamic evaluation, this cleverly handles noisy because of this parameter only, not because of the this complicated formulas and all. Okay. And overall, we are trying to minimize this particular index value, and the for which value K value. So for which K value, so this index value is minimum. So that is considered as a best output for your the algorithm. Okay. So as mentioned, what is the different parameters? So the sets one, there is no noise in the data. If there is a noise in the data, some noisy are sometimes greater than one also. Okay. Similar lines, there is another person, Davies and Bouldin. These two persons have built another index, and its index is called Davies and Bouldin index. Davies and Bouldin index. Okay, so what they are doing in this case, so they are finding this Davies and Bouldin index, where K is the number of clusters. For which number of clusters? So this is having the minimum maximum value. So if you see for which value is having a maximum value, so for which K value it is having maximum value, so that we consider as a cluster. So how they are finding out for 1 by K, where K is the number of clusters, summation over I is equal to 1 to K and the D of I. What is the D of I? So D of I is considered as the maximum of R. So what they define R? Where Si and Sj. If there are two clusters, Si and Sj and M of Ij. Si is the measure of scatteredness within the clusters. This is intra-cluster distance equal to intra-cluster distance, and this M of Ij talks about measure the separation between the cluster centroids T and Sj. This talks about the two cluster centroids. This talks about the well separatedness. The numerator talks about the compactness of the cluster, and so usually we are trying to minimize this. So we are trying to, this should be maximum. The compact should be. So this is we are trying to minimize this, because this should be minimum and this should be maximum. Hence, the overall R of Ij, we are interested to the minimum, for which value is the minimum, and among for each minimum for among all this you will have set of R of R12, R13, R1. So there are three clusters. Suppose there are 3 clusters. This is 1, 2, 3. You will get R12, R13, R23. You will get the three. For R12, you will get one value. For R13, you will get one value. R13, you will get one. Among all, which one is the maximum? So that is the among all. That is a. So like this, you can find out the sum of for k is equal to 3. For k is equal to 3. So for k is equal to 3, so you will find out the 1 by 3 summation over I is equal to 1 to 3 d1 plus d2 plus 4. It doesn't make any make sense if there is a d is equal. There is one cluster. The standard deviation of your other cluster will be the this one. Because it is the SI plus there is only one cluster, so this applicable for only I is equal to 2 onwards. There is doesn't make any sense. It's 2. So I hope you understand. Because there is if there is only k is equal to 1 means there is no cluster. There is only single cluster. It doesn't make any sense. At least you should have 2 clusters. K is equal to and for k is equal to and for the k is equal to there are 2 clusters. So there are only one possibility or 1 2 only. So you have to find out for which value of for k is equal to 1 2. It doesn't make there is no maximum comes. There is no this won't play any role. But if there are 3 places, there are 3. So among R12, R13, and R1, which one is the maximum? This value will put it here. Okay, that is the DI. The DI will be talks about the maximum across all these ratios. The maximum across the ratio. Where are the ratio? What is the ratio talks about? The ratio talks about the for which values. Basically, it's kind of, if you see clearly, it's a some sort of. You see, it is some sort of the ratio index here. It's some sort of ratio index only. So basically, you have got it right. For every possible, for every k value, you are finding the ratio index. You are summing those ratio index. It's a summation of the ratio index. You can visualize like that. Okay. So ideally, we are trying to minimize this. And for a lower dB value, the better the separation of the clusters and the tightness inside the cluster. For dB index, for which dB index value, so your function is having least value. So for this k value, that's the optimal k value. Like this, we can use this dB index to evaluate the clustering algorithm. Now let us come to the. So there are some of the references. We have taken this content from some research papers. Now let us come to the cluster validity index, the application where we can use these applications. Okay, so how we can make use of this cluster validity indices. Okay? So what we did here, so in this case, so what we can do this, if you see here, there is a cluster value indices. So what we did in we have used this combined this cluster validity index with the k-means algorithm. That's one possible way. So what we can do, sorry. So we can combine any of the cluster values with the k-means algorithm. So what is the output? So here you need not to fine tune k value, because when you are combining the cluster values in the k-means algorithm, so what will happen? K is equal to 1, you will get CVI value. This one k is equal to like this. If it is a ratio index, for which value, for which k value, this index value, so that is a k value. Best k value for the k-means algorithm. Here you need not to use the knee approach. When you are properly integrating this, so when you run this algorithm, you need not to worry about so what could be the k value for this, and the output of this integrated k-means algorithm. When you are combining this k-means algorithm with the cluster value indices, it automatically figure it out. So what could be the ideal value or what could be the optimal value, k value for your k-means algorithm for the given data set. So that is the beauty of this set. So like that, we can use it. We can combine it with the help of the k-means algorithm. So that's what we can see here. Same thing what we did in the, see here. See the second point, the integrated k-means algorithm is applied over the whole training data. Means So the first point, we have integrated k-means algorithm with the k-means cluster value indices. So what we did, so this is a part of our research. What we did, we combined the k-means algorithm with the cluster value indices. So what is the advantage? You need not to fine tune the k value. So that the biggest bottleneck with the k-means, the partition based algorithm, that is subsidized. So like this, you see these two plots, because we have compared with the, so we have run the k-means algorithm with the intra-inter ratio and Dune index and dynamic value indices, and we got the best k value. The best k value for a clustering algorithm is 48, 83, and 39 cluster it has created. The reason why we have integrated over here is, the reason for integrating this algorithm is the one of the neural network is, maybe by this time you all are familiar with what is the artificial neural network. It has a layers, so input layer and output layer, and by default it will have at least one hidden layer. So if you look at the RBF in one of the neural network, it will have the same structure. It will have one input layer, one output layer, and only one hidden layer. But what is the problem with this network is, uh, the problem is the size of the hidden layer is grows exponentially with the size of the data set. If the size of, because the number of neurons in this hidden layer of this RBFN is equal to the number of samples in your training data. So hence the complexity of this network with the number of neurons will be increased. So we want to cut down the size of this hidden layer. So what we did, so we have applied the, on training data we have applied clustering algorithm, but we don't know how many groups will be there. Am I right or not? Because that's that's the duty of the clustering algorithm, but we don't know whether the clustering algorithm, suppose I have used the k-means, maybe it has created some clusters. If I run for k is equal 10, it will create 10 clusters. For k is equal 30, it will 30. Whether the 30 clusters have been formed, are properly formed, or I don't know. How do you evaluate? So we can evaluate using cluster value indices. But what we did, we integrated these. We have used inside the k-means algorithm, we have integrated cluster value indices. So what happened? So it automatically find out the best cluster. The best cluster. How do you define the best cluster? The clusters which are very compact and which are well separated among each other. So that kind of cluster, when that kind of clusters is being formed in your data set, obviously the cluster value indices will be either minimum or maximum according to the your kind of this CVI you will choose. Cluster value index you will choose. But if I choose, we have chosen for your experiment are using all the indices, of course. But if I choose a ratio index for which value, so we got a minimum value, so that we found that, so that is the best clusters have been is there for in our data set. Hence we found that, so there are such kind of groups are there. Okay, for each group we have represented as a one cluster head. So instead of having, because we know that what is the beauty of the clustering, the whole group can be represented by cluster head, because all the properties are very near to because why we group together, they are nature, they have similar characteristics, they have similar properties. It means the one sample is nothing. If I know the sample, what is the characteristic of one sample, I definitely know what is the properties of the remaining sample, because because they are very close to each other. We can say that they have similar properties. So when I know that the properties of these all the group members are similar, I can able to represent with the help of only one single sample. So that is sample is called the cluster head sample. So that's what we instead of having that way we cut down the number of neurons by creating the number of cluster, and that too by using integrated k-means algorithm by combining the cluster value indices. Okay. So further, if you want to proceed further, you can. I will share these slides and you can refer it. So these are some of the plots that will show how the ratio index values so far, and what is the Dune index, the DVA index values, and I'm putting all these things together. This plot shows. Okay. So this way we can use the cluster validity indices for along with the your clustering algorithm to reduce the size of your RBF. Okay. So then another way we can use is what we did in the case the way if we apply in this process, what will happen? Suppose if a cluster centroid is near to this, suppose if a cluster centroid is, suppose where is the not able to. I am not able to draw here in the PDF. Okay, let's see. So I'm not able to draw on the PDF. No issue. So if you see, there is a separate, there is a line. Okay, there is a hyperparameter. There is a decision boundary behind the blue and red line. Suppose if my cluster head is near to the boundary line, what will happen? If the cluster is boundary line is, then what will happen? So this cluster will have, what will this cluster will have a subcluster which is actually a mixture of, because some samples of other clusters will also be a part of this. That's what it suppose. That's what it is representing the right side of this figure. It means that so this particular it's supposed to be either blue or red, but it is having a mixture of both blue and red. Means it is improper cluster. We are not done properly. Why it is happened? Because we have this happened because of your clusters are being formed. The cluster heads are near to the decision boundary. So how can you overcome this? If to overcome this, what we did, so we can, another way of solving this problem is we can apply the same approach inside your class data. Means what you did, you take out the red samples out and blue samples out and apply this procedure, same procedure. In the earlier case, we applied it on the whole data, but now we apply it in the class level data. Means you take out the red samples out and you apply this procedure, you take out it, then this kind of problem won't occur. Of course, that is one of the advantage. Another advantage is in the computational point of view, but there is a less data samples are there, you can finish, your algorithm will terminate very fast. I mean, in computational point of view, it is benefit from. The same process. Then somewhere we can also use in what we did. So this is like k-means and k-midwives algorithm. So this is some of the algorithms which are based on the bio-inspired or nature-inspired algorithms. So like the PSO, particle sum optimization based clustering. So clustering is one of the, we can form it as an optimization problem. Of course, definitely it is an optimization problem. So this optimization problem we can solve it using a PSO. So in the process of solving this optimization problem, so we have to define and a good activation function, a good fitness function, a good objective function. Okay. So as a part of the fitness function, the objective function, so we have used this well separated compactness and separability of the. This talks about the clustering algorithm, like how we can define the compactness. Will talks about the intra-class, and the separability will talks about the intra-class distance. Okay. So like this, we have defined this is separability will talks about the distance of 2 points, and so like we have defined these two compactness of the cluster means talks intra-class, and separability talks about the distance to the cluster. They should be, so ideally we can also use the cluster value indices as a part of the fitness function to get the better clusters. Okay, so this is another application where we can use this cluster value indices to get the better clusters. Okay. So that is all about how we can make use of cluster valid indices, and the two applications I discussed, and those two are the general articles. I mean, where we have used the cluster valid indices for effective clusters. Okay, so that's all about the cluster valid indices and applications. So with this, my session is over, and if you have any queries, you can raise your question and.
Participants, please come forward for
So if you have queries not only regarding to this particular topic, you have any queries regarding the supervised, unsupervised learning or ensemble learning, whichever I taught during this FDP, you can ask any question relevant to all these topics.
Good evening, sir. Sir, I am audible, sir?
Yes, sir, you are audible, sir. Please go on, sir.
Sir, can I ask question?
So
Professor Ramlinga Swami, sir, a participant is ready for asking questions, sir.
So what is the application of density connectedness? No, so there is no application. Okay, so the question is, so we have different kind of terminology related to the density based clustering. So how this density based clustering algorithms will create the clusters? What are the clusters? A set of density regions. Okay, so question is, how do you identify the density region? To identify the density region, we have defined three measures like directly density reachable, and directly density connected. So set of this density reachable or density connected points is called a one cluster. Set of such point, because those points are, every point in that is a core point. I mean, so because when you're there is a sequence of core points exists, so it forms a what you call some kind of cluster. Okay, what is, how do you define a cluster? A group of people, okay, a group of data points together. Okay. So that we can already define using minimum number of points. As it has become, when it is more than minimum number of points are there, because it's eligible for the core point. So it's a set of such core points will form a density region. Okay. There is no application. I mean, this we will make as a base to create the groups or clusters. That's it. ML2P0 is Dr. Mishra. Okay, Minati Mishra. I hope I answered your query. If you are still, you can. I'm happy to answer your queries.
Sir, can you hear me?
Maybe I didn't see it. Maybe I just now saw your query. Yes, guys, if you have any queries.
Sir, can you hear me?
So these are the references and the research papers I have taken from these research papers. You can refer it if you want it for proceed further.
Sir, Mr. Praveen Kumar Singh has been trying for some queries, sir.
The CV, one of the CV application is you can integrate with the k-means or any clustering algorithm, so that you will, especially in partitioning based algorithm, but in case of DB scan and all, this is not the hyperparameter. You don't have much benefit by integrating, but we can use it. I mean, suppose in case of DB scan, how we can make use of, but for a DB scan, so you are using DB scan, right? You are using DB scan. What you can do, you run this algorithm with some certain hyperparameters will be there. Okay. And for with this, what is for these hyperparameters? So this is some epsilon is the hyperparameter or something else. For DB scan, what is the hyperparameter? Yes, EPS is the hyperparameter. So EPS, for EPS is equal to 1, EPS 2, EPS 3, and EPS 4. Like this, then we can say that. Then this is a what is called some ratio index, CVA index value. So any of the CVA index value, you will plot the graph. If the ratio index for which epsilon value this index is value means, so that is the best value for that your algorithm. So like this, you can use it for the fine tuning of hyperparameters of your any clustering algorithm. We can, that is another application where we can use this cluster validity indices, because this will ideally gives what talk about So with the ratio index, if the ratio index, we are trying for the minimize this value, right? But for which value, for which value of this algorithm, suppose epsilon is equal to 5, so your index means for this is the optimal value for the epsilon is equal to 5 because it is giving the best result, because low means at this point this algorithm will have compact clusters and well separated clusters. Compact cluster will talks about the same with respect to single cluster. The well separatedness will talks about the among the clusters, multiple clusters. Talking about the multiple clusters, it's giving you end up creating such kind of clusters. Hence, so we can fine tuning of the hyperparameters of any clustering algorithm also we can make use by plotting this kind of plot. We can make use of it. This is another application where you can use it.
Sir, I am mentioning my question in chat box.
Tagging neural network. So what is, sir, can we apply CVA and K-means for data pre-processing with any type of PF prediction? Not getting your query. Let me wait. Let me answer. Okay. Somebody, okay. Sir, can you apply CVA and K-means for no, for data pre-processing with any type of ANN for prediction? Okay, the reason why okay, yeah, I answered. I understood some extent. I understood the question. So the reason is it's not general for all the ANNs, because in RBFN, because the size of the hidden layer, because there exists ANN for with the 3 neurons in the hidden layer, 5 neurons in the 10 neurons in the release is possible. But because if you take ANN, there exists 10. Suppose you take simple ANN, input layer, hidden layer, and output layer. So you already know what the size of input layer is equal to number of features. Output layer is number of classes. But if you take any hidden layer, so you can with single hidden layer with sufficient number of neurons, you can approximate any this universal theorem. Okay. So that's one way of doing. But this number of neurons, how many you have to keep it? Just you can. It's a fine tune. You have to fine tune it. Sometimes you can get 10. You can get it, or you can get 10 or 15 or 15. But where in the case of RBFN, the size is fixed. The how many number of you have to keep in the hidden layer of RBFN is fixed. It is equal to the size of your data set. We try to reduce this, but this is not applicable for the ANN, because ANN mostly you require few number of neurons. So it's of no use of applying this. So KNN regression model. KNN, how the KNN functions, if you see, take you see the KNN. So this is a one sample, okay? This is one sample, this one sample, and this is sample. Now so I know that the class label of this sample is positive. The class label of this sample is positive, and this sample is positive, and this sample is positive. And there are another samples which are here, and this sample is the negative and negative and a negative, and this is negative. We know it's class label. And a new sample came. A new sample came suddenly here. A new sample came here. Now, then what I do? What is the class label for this? I have to predict it. So what the KNN does? Suppose K is equal to 3. First, it identify the K3 nearest neighbors. Suppose this is the first nearest neighbor, and this is the second nearest neighbor. This is the third nearest. This is the first, second. I am assuming. So what is the class label of the first nearest neighbor? Positive. What is the class label of second nearest neighbor? Positive. What is the class label of third nearest neighbor? Negative. So it's negative, I think. It means that among the which one is the majority, it will apply the majority voting. It will get the output of this is the kind of the ensembling sort of thing. So if you see, so that's how the KNN works. So it will find out the K nearest neighbors with respect to this point, and it will identify what is the majority class label in the surroundings. So accordingly, it will classify the things. But regression, I don't think we can use it for the regression. Yes, let me answer another queries. So good to, sir. Can you tell me the process of how ML can identify and guess the user interest while interacting in YouTube or any websites while searching the any content? It's a recommended system. Okay, it's a topic of a recommendation system. Okay, so based on our interest, so it will recommend the similar fees, similar characteristics. Okay, it's altogether it's a recommendation system. Okay, it's altogether different topic. It will cover in the recommendations. Okay, so how by looking at the previous history of your model, so what we can use, like suppose what you can do, you can, by looking at all your previous information, suppose you have a previous information, if you have all the previous information with you, so you have all the log information when you are browsing Amazon with some, what we can do, so how it does.
Sir, here my question is how the user data can be handled in the
Suppose you
server
have,
and
when you
how
are,
it
suppose I
is
have
interacting
logged
with
into Amazon account with my
millions of
some
people at a time.
RML Swami something. Okay, so I have some my log information with me, right? What are my previous history? They will, yeah, what the Amazon will keep log. Okay, so on top of this log, they can run some kind of what you call the prediction model. Okay, they will apply some kind of models, recommendation. It's called a recommendation system. These are altogether recommendation systems. So what they do, they will identify what is your characteristics. Okay, so suppose every time you are preferring an item which is having a 3.5 rated, or every time you are searching for a kitchen item, okay, they will capture your interest. By using these models, they will capture the interest, and based on these interests, suppose if any product is matching these interests, so they will try to pop into your, when you are browsing, they will pop into your either browser or in any of other window and sort of. It's called this especially, it's altogether it's different, and it's called
Machine
a,
learning server is
special, it's recommendation
dynamically running
system.
with the user interest. Sir.
Recommender system. So it's a huge topic. So with ANN for prediction, we cannot, ANN we cannot use it. So suppose if you because in ANN mostly we can use it with the hidden layer, or you can use multiple hidden layers also. Your problem is solved like that. You can use it multiple hidden layers. You need not to have single, but in case of RBF, you have a restriction that you have to only have single hidden layers. That is the problem. Otherwise,
This
in
conference will
ANN you have
now be
flexibility to
recorded.
extend multiple hidden layers. So there you can solve the problem using that approach. I hope I answered your query and this one. What is this ML2P173 by the way? Hello there. So any more queries? So still 5 minutes are there.
Dear participants, please come forward for interaction. We have 5 more minutes for the day. Sir, I believe everyone is quite confident with the concepts, sir. If you can permit, we can wind up the session, sir. Dear participants, please be informed that attendance link has been posted in the chat box. If you have any queries left over, you can stay back, else you can take rest for the day. Thank you very much.
Hello. If you don't have any queries, then I will wind up my session. Okay. Thank you and happy evening.
Thank you, sir. Thank you very much, sir.
Praveen Kumar, I answered your query, I think. Not satisfied, you can. Praveen, are you there? Test link, what is this test link? Maybe it is.
We request participants to come forward for interaction. We have 2 more minutes to go.